this video, in this summary video, I'm going to talk more about some of the topics that I handpicked from chapter 6, and its title is Quality Improvement and Control Tools. So in this chapter, we see more about the implementations of Six Sigma and total quality management, how we can incorporate all those cool methodologies into our manufacturing and service systems to keep our operations in statistical process control. Okay. So as I said, this is a summary video. I'm not going to talk about the entire chapter 6 topics. You should study chapter 6 lectures and the materials that I posted on Canvas. So these summary videos are meant to be, summarizing some of the challenging or maybe complex topics that I consider them as such in your textbook chapters. So there will be two summary videos. In the first video, in this one, I'm going to talk more about why we use statistical process control and how we use it, what's the main philosophy behind it. And in the second summary video, I'm going to dig further on how to use statistical process control charting techniques so that we understand whether our operations are under statistical control or not. Okay, so let's get started. As we study in chapter 5, we understand that quality management has to be incorporated in the entire supply chain. What I mean by that, so you have to be looking at your entire supply chain, starting from your suppliers, all the way down to your customers, the entire operations between, remember, raw materials into selling them to your final customers and collecting the feedback from your customers and incorporating it into an entire system. You have to be mandating quality control methods in the entire supply chain management, right? If you don't do it that way, then you do not have any coordinated or integrated quality control mechanism in your supply chain. So this video is, and this chapter is more focused on how can you enforce these quality control methods in your operation. So let's get started with this cool statement. Say, so, okay, I understand that the variations are bad for quality, but what should I do? Well, remember, there are several causes of variability. That's why we adopted those philosophies like Six Sigma and total quality management into our operations. It has to be a complete philosophy that you use to tackle those sources of variabilities. You should provide room for natural variations, but you should detect the assignable causes right away, right on the spots. And I'm going to talk more about what assignable causes and what common causes of the variation. So we do have two main categories of variation. In the common cause, we understand those variations that those are purely random. So you cannot really control everything, right? In your life is complex. There are many different factors. You cannot really, although you like to plan in very nice details of your day, right? I mean, you fail to plan some of the stochastic events that are happening on your daily lives. Well, you should, incorporate some common cause or random variations into your life, and those are some of the surprising points that maybe you enjoy or maybe you just don't enjoy them very much, but that's part of the life. Okay, so if you look at your manufacturing or service operations, so common cause variations are typical and you should permit them to happen, right? That's why we do have lower bounds and upper bounds on some of the certain specifications of the products or services that we offer. For example, if you go to a hospital and you know that there is going to be a wait time, but you know that it might be hours or it might be just minutes, right? Especially if you go to emergency room, this is changing very much. So some of those variation is due to common cause when maybe doctor is taking some more time to be precautious on certain patients, or maybe doctor is not having a good day. Due to those simple changes in the operations, you might see these common causes. Assignable causes are, on the other hand, are very important, and we should be detecting these assignable causes in our operations. What do I mean by that? Again, let's assume that you are running a car manufacturing company, and then you have the assembly line, and all of a sudden you see that maybe you are in the paint assembly line, you see that you are not getting the right paints or the colors that you want on the cars, and maybe it is due to a machine that's about to break down, or maybe several of your employees are not motivated, they are not really keeping up the speed. You should be assigned that variation to the right source. That's what I mean by assignable cause. We should definitely be preventing these assignable causes, and the first step to prevent these is to catch them on spot without even waiting further, right? It is better to catch them after we see an error on a single car, rather than waiting to see that assignable cause happening on hundreds of different cars, right? So statistical process control charts are going to help us detect those assignable causes. All right. We usually have a variable that we measure the quality characteristics on, and we work with that variable to see whether it is under statistical process control or not. So when should we use them? Well, that's a really good point. So we should not really be using them in all sets of our operations, because those are time consuming and costly and sometimes just redundant. But these are the main points where we might need statistical process control charts. So number one is at the beginning of a manufacturing process to check that the raw materials and the components used in the process are defect free. Well, if you have seen a manufacturing environment, you know that before the operation starts, they accept raw materials into their facilities, right? And when they do that, they should be doing some random checks on the parts that they accept, or maybe they check them all, depending on how important these raw materials are for them. And when they do that, they should be implementing statistical process charts to make sure that the parts that are coming from their suppliers are under statistical process control before they even start their operations. And number two is before an operation such as painting or packaging that might mask defects. Yeah, these are very crucial operations. After some use, customers might understand that might detect that the products or the services that they are using are actually defective, right? So before you do any painting or packaging or any other operations, or maybe if it is like software that you're selling to the customer, you want to make sure that before you provide graphical user interface, you want to make sure that the source code is working bug-free. All right, number three, where it might be used before costly or irreversible operations are performed. So this can be tied to number two. It is a very generic explanation, but before your products or services go through a very expensive operation, you want to make sure that the parts or the services that you're providing for the next step are defect free. Or number four, before delivery in the case of a service. So that's very obvious. That doesn't really need further attention. All right, what are the types of control charts? So there are multiple types, but for variables, we are going to be using two main charts, the mean chart and the range chart, okay? So if you would like to make sure that your variable charts or are under statistical control, you would like to draw this mean chart and range chart, and you want to make sure that those are both under statistical process control. And in a minute, I'm going to define what statistical process control really means, okay? But you have to draw both of them to be able to conclude that either your operation is under statistical process control or is not really under statistical process control, okay? This is very important. You have to construct both of them. Okay, so what do I have in my statistical process control chart? So both in mean chart and R chart, so I'm going to use these terms interchangeably. I'm going to either call mean chart a mean chart or X chart, okay? And I'm going to be using range chart or R chart interchangeably. So don't get really confused with that. What do I have in common? I do have a center line that I want my observations to follow. It is going to be the ultimate middle point that I want my observations to fall on, right? And I do have an upper control limit, and I am going to have a lower control limit in my statistical control charts. So basically, is going to look like this, and my center line is going to be in the middle. My upper control limit is going to be on the top, and my lower control limit is going to be on the bottom, right? So it can be same for mean chart or R chart. And what I want to do is I want to look at my observations to see whether they are following a certain trend or are they crossing this upper limit or lower limit. If they do, then I'm going to give a warning to the system that, hey, you know what, my process just got out of control, out of statistical control. That is the main idea behind statistical control charts. Well, how do we do that? I mean, I'm going to show you that over an example in the next video. But before I really move to that point, let me explain further where this comes from. You remember in chapter 5 summary video, we talked about Six Sigma operations, right? Six Sigma quality management concept or philosophy, whatever you want to call it. Well, actually, if you think about it, right? So if you are above 3 Sigma, above the mean, and 3 Sigma below the mean, what you are doing is you are capturing 99.9996% of your operations, right? So if you convert it into numbers, every million that you produce or you put together as a service, 3.4 of them are just going to be out of this range. Okay, that is the main concept behind Six Sigma, right? Therefore, we tend to represent our statistical control charts like in this fashion, and you can think about our upper control limit chart as mean plus 3 sigma, and our lower control chart line as our mean minus 3 sigma zone that you can label them like that. So you want your operations to fall between upper control limit and lower control limit. So let's take a look at this chart then. So this is a pre-drawn control chart. I'm not sure whether this is a mean chart or R chart, but it doesn't matter. Let's assume that this is our mean chart. What's going on here? Let's take a look. We do have upper control limit here, and we do have lower control limit here, and we do have our center line here. These dots or these diamonds are going to be our expected or the average observations of each sample. So we got samples of data that we collected, we took the average of them, and then we plot them here on this chart, right? Let's assume that this is what's going on. So if you look at these blue set, right, the first 1, 2, 3, 4, 5, 6, 7 data points, you see that those are randomly scattered around the central line, which is really good. I mean, this tells me that all I do have in this process is just random cause, right? There is no assignable cause here. But take a look at this green set of diamonds. What do you see here? So the first 3 maybe are looking like those are randomly scattered along the center line. But if you form a trend line with the rest of it, you see that there's a positive trend here, which indicates that something in my process is pushing my average observations towards my upper control limit. And the last 3 actually is just a proof that this process is no longer under statistical process control. Something is going on, something that I should really take a look at. Maybe I should stop the process and see what's going on. Maybe it's a breakdown machine. Maybe my people are not really following the instructions. But this is really, maybe after 1, 2, 3, 4, 5, after the 5th point, you could actually see this very carefully and very easily that the trend is being formed, right? So you might stop the operation here, but if you stop it here in the 2nd point, what's going on? You would already produce these products or services, and it already costed you much. So the sooner you detect this system, the cheaper you're going to get out of this mess, right? So these are the main points that we are going to look at after we draw these charts. But again, this is just a proof that this process is not really under statistical process control. If you had this chart just fine, let's say this is the mean chart, and you want to conclude something about this process, you have to draw the R chart later. And then if the R chart and the mean chart are both under statistical process control, only after then you can say that, okay, my process is under total statistical process control. Okay, so in the next video, I'm going to show how to calculate, how to draw these charts.